A quadratic function will have the following notation. It's going to be some function of x, and that's going to equal some coefficient of a, that's called the leading coefficient, multiplied then by x squared, remember x is the variable, plus some coefficient b multiplied by x, plus some coefficient c. Now, coefficients are numbers. They're going to be values. Whether they're negative or positive, that does not matter at all. All right. Now, every single quadratic function can be written in this form. So, for example, if I had, let's say, f of x is equal to 2x squared minus 4x plus 5, that is indeed a quadratic function. I have an x squared term, an x term, and a constant term. The coefficient, the leading coefficient, is a 2. The b value is actually a negative 4. Always keep that sign in the front in mind. And then the c term is going to be positive 5. How about another example? How about if I had f, now it doesn't matter if it's f of x or g of x or h of x. So I'm going to just write h of x this time. And imagine I have something like 1/2 x squared. Now, is that a quadratic function? If I could speak, that'd be nice. Is that a quadratic function? It turns out that it is. You might say, well, wait a minute, what? How's that a quadratic function, Andrew? It's missing all this stuff. Well, it turns out that all this stuff is really not that important when we're describing quadratic functions. What's the most important term is this, x squared. Okay? You have to have at least x squared in your function. At least x squared. And you can't have actually anything greater than x squared in the function. So as long as you have that, that's the essential characteristic of a quadratic function. Okay? And it has to be a positive 2. Can't be a negative 2. All right? So that is indeed another example of a quadratic function. Now, how about something like this? Let's do g of x, just to change it up a little bit. G of x is going to be equal to 7x minus 4. Is that a quadratic function? What do you think? It is not, right? It is not. The reason being is because we do not have the defining feature of having an x squared term. We only have x in here. There's no higher power of x, right? We need at least x to the second power. So that's actually an example of not a quadratic function, right? What about if I gave you f of x is equal to then 3x cubed minus 7? Is that a quadratic function? You got it. Nope, it's not. The reason being is because we have now a power of 3. You cannot have a power of 3 in a quadratic, actually. This is actually called a cubic now. It's a cubic function. It's going to look very different. It behaves differently. And let me give you one more example. Let's make it a little bit more challenging. So imagine if I had something like x times x minus 3, plus 2 or something. Is that a quadratic function? What do you think? Did you say yes? Then you are correct. Nicely done. Now, you might say, well, wait a minute, Andrew. You said that has to be an x squared somewhere. I don't see it. I just see x to the first power. Well, that is true. When we visually inspect it at the moment, all we see is x to the first power. However, if there is any type of algebraic manipulation that you can do to show that it is x squared, then you must do that algebraic manipulation. For example, what I can do is I can take this term, x, and I can distribute it to each of the two terms inside of that binomial, right? That's just simple distribution. Now, if I do that, the result becomes this. X times x is going to be x squared, and then x times a negative 3 is going to be negative 3x. And then we're just going to bring down the positive 2. And wait a minute. This now looks like a quadratic. So sometimes you can think about it as there's a hidden quadratic in here. Okay, so upon first inspection, it's not good enough to just look at it and make a quick determination in some cases. You may have to do some algebraic manipulation or some algebraic massaging in order to see the potential quadratic. Okay, so just be careful. Just think, even if I don't see it right now, is there any algebra I can do to maybe find the quadratic. Now, one more important thing that we see on the screen, and this at the top, this form of a quadratic function is generally called the standard form. The standard form, okay? There actually are other forms of the quadratic function. Now, they all wind up being able to be algebraically massaged to look like each other, okay? It's getting a little bit strange. I'm going to stop using the word massaged. Manipulated, I don't know if that's any better, but anyway, we can manipulate the standard form and produce something called maybe the vertex form, all right, or something called the factored form. There's three main forms, okay, and this is the standard form. So let me actually quickly describe the vertex form. The vertex form will have the following notation. It'll have a leading coefficient of a, and you're going to multiply it now by a squared binomial. And inside of this binomial, we must have our variable x, and it turns out that we're going to be subtracting from it some constant h value, some constant. All right, h just represents a constant, just like the b and the c did in the standard form. And then we're going to be adding to this some k term. And again, that just represents some constant term. Now, in this case, it does look different from the standard form. Okay, this, so I'll write it on the side, is the vertex form. Okay, and this is beneficial because it actually can tell us something about the vertex of a quadratic. Okay, now, not to lose sight, but what do I mean by vertex of a quadratic? Well, we must keep in mind that quadratics will look like one of these two graphs. It'll look like one of these two graphs. So quadratic functions produce parabolas. Right? Say that with me. Parabola. 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 It'll produce a parabola. Okay? And a parabola can either smile at you or it can frown at you. One of the two. Okay? Now, if it smiles at you, your leading coefficient, remember in the standard form we called a the leading coefficient. In the vertex form, a is also the leading coefficient. If a is positive, okay, if your leading coefficient is positive, then it smiles at you. And if the leading coefficient here is going to be negative, well, then it's going to frown at you. Okay? But one thing is very unique is that when we look at the quadratic function also, it'll have this kind of U-shaped, pattern to it. We got to be very careful, though, that it doesn't look like this. This, you might see something that might look like this. That's a terrible drawing. Let me try to make that a little bit better. Something like that. That is not a quadratic. Okay? It's too flat. All right? Too flat. It has to have this nice kind of hairpin turn. All right? Now, there's ways to graphically analyze quadratics. We're going to do that in a later chapter. This is just trying to get a feel for what they look like. All right? So graphically, they're going to look like a parabola. A parabola is basically this shape right here. It's either a smile or a frown. And the smile or frown will tell you whether the leading coefficient is positive or negative. So the benefit here of the vertex form that we have above us is that the h and the k terms will tell us something unique about the vertex. The vertex is going to be either the lowest point on the smile, okay? It's on the positive leading coefficient, it represents the lowest point, or the vertex will represent the highest point on the frown, or on the negative leading coefficient version, okay? And I'm going to get to vertex form in a later video, so that's good enough for now, but I just wanted to try and introduce that. Okay, so this is another form of a quadratic function. So if I were to give you, let's say, a function down here of f of x is equal to -7 times x minus 1/4, squared plus 32, is that a quadratic function? And it turns out that it is. Okay, this follows the vertex form perfectly well. It follows it perfectly. So now let me quickly show you the relationship between the vertex form and the standard form. So let's suppose we have a vertex form. I'm going to try to make it simple. But let's say we have 2 times x minus 3 squared plus, 4. Okay? Plus 4. And what I'm going to do is I'm going to try to take this quadratic function, which is in vertex form, and I'm going to try to convert it into standard form. Remember before I said that these are all representing the same function, they're just algebraically manipulated a little bit differently. So what I can do first here is I would first apply PEMDAS, right? Inside the parentheses, I cannot combine x and minus and a -3. There's just nothing to do. So the next step then is to move on to the exponent. And what I'm going to do is I'm actually going to rewrite this. So instead of writing this as x minus 3 squared, I'm going to write that binomial twice. And it's essentially multiplied, right? So it's going to be x minus 3 times x minus 3. Okay, so I'm going to leave it just like that. Now, this may look familiar. The next thing I'm going to do is I'm going to FOIL. Okay, I'm going to look at these two. Since it's really 3 terms here that are multiplied, you're taking 2, multiplying it by this crazy thing, and then multiplying it by that crazy thing. I'm just going to work with the crazy things first. I'm going to multiply those two. And it turns out that we can FOIL this. Okay, so first I'm going to take x times x. All right, that's going to be x squared. Let's write that down, x squared. Then I'm going to take x times -3. So that's a -3x. Let me make that a little bit neater, -3x. Then I'm going to take -3 and multiply it by x, right? I take the next term or the last term here and multiply it by the first of the second binomial. So that's going to be -3x again. And then last but not least, I'm going to take the -3 and multiply it then by the other -3 for a total of a +9. Okay? So this whole expression here basically simplifies. I'll give a little bit more space. It basically simplifies down to this. Okay? I'm going to just copy everything down. So 2 over there and then a +4. Okay. So now what I can do is I can combine some like terms in here. So just to simplify this and to maybe just try to make this go a little bit quicker, I can combine the -3x and the -3x, right? If I add them together, that's a total of -6x. So let's plug that in. So it's going to be a -6x. Okay, and I'll move everything now nice and close. So I can't, remember I was applying PEMDAS there. I was doing an operation inside of those parentheses. So now I can't really do anything else inside the parentheses. So now I'm going to look to do a multiplication, and now I can do a distribution. Right, I'm going to take the x times the x squared times then the -6x and then times the 9. Let's write that result on out. So it's going to be 2 times x squared, which is going to be 2x squared. Then 2 times -6x, which is going to be a -12x. Then 2 times +9, which is going to be a +18. And then, lo and behold, bring down the 4. Now, can I combine anything? Sure I can. I can combine the 18 and the 4, and that will be now 22. So that'll be a +22. And OMG, OMG, what do we have here? We have the standard form. Okay, that's standard form, right? This is our A is 2. Oh, wait a minute. That was also our A here in the original vertex form. See? So I have my A here, my B is going to be -12, and C was +22. Now, lastly, I'd like to introduce the factored form of a quadratic. Okay? A quadratic function in factored form will look like this. It'll still have a leading coefficient of A, and then we're going to multiply it now by 2 factors. It's kind of similar to the vertex form, but not exactly. We're going to have now 2 binomials here, where we have our variable in each term, and we're going to be either adding or subtracting. It doesn't really make a difference, but I'll just write it as a subtraction right now, and we're going to be subtracting some constant. I'm going to call it R1, and I'm going to call this one R2. The reason being is because these numbers will, over time, when we'll do more factoring in a later video, but these will represent the roots, okay, of the quadratic function. This is basically going to be locations where the quadratic function will cross the x-axis. Again, we'll get to that in a later series of videos. So if you're watching this on our website, glazersguide.com, you'll kind of see you're in the quadratic chapter right now. If you look down just below, we're going to get to some factored stuff very soon. Okay? So for right now, I just want you to be able to recognize the forms. All right, so this form is going to be called a factored form of the quadratic. Okay? So now some examples, right? If I were to, let's say, write an equation like this, f of x is equal to x minus 4 times x plus 2. Okay, is this a quadratic? Yes, it is. It is indeed a quadratic, right? And it follows the factored form. The only thing, though, is you might say, well, wait a minute, where's the a? Where's the a? I don't know where that is. Well, it turns out that there is indeed an a value there. It's actually a 1. If there's nothing in its place, you can always put in a 1 there, okay? Because multiplying by 1 doesn't really do anything in terms of changing the nature of that function. All right, so the leading coefficient here is actually a positive 1 in this example, okay? And to even show you the connection now to standard form, I can FOIL this out, right? So I can now take x times x, we multiply the first two terms, so that's x squared. Then I'm going to take the outer two terms, so I'm going to take my x and multiply it by positive 2, so that's a positive 2x. Then I take the inner two terms, so that's going to be negative 4 times x, that's going to be a negative 4x. And then I take the last, so it's negative 4 times a positive 2, which is a negative 8. And then I'm just going to combine some like terms, and I can rewrite this as x squared minus 2x minus 8. And lo and behold, that follows the standard form perfectly. Okay? So as you can see, all these forms can relate back to the standard form. You just have to do a little algebraic manipulation. If I had a quarter for every time I said algebraic manipulation, I would probably have $7. Okay, I'll give you one more question. So let's pretend I had something like this. Let's pretend I had something like x times x minus 2 times x plus 1. Is this a quadratic? What do you think? Pause the video and try to figure it out. See if you can maybe mathematically manipulate. Oh, now I got $7.05. See if you can do that. And yeah, pause the video. All right. So did you say it is a quadratic? That's okay. It's actually not. So it's not a quadratic. The reason being is because now when we FOIL this term out, right, when we FOIL it out, we can do that right now, x times x, let me make that a little bit neater, x times x is going to be x squared. The x times then positive 1 is going to be a positive x. The negative 2 times x is going to be a negative 2x. And then last but not least, negative 2 times a positive 1 is going to be a negative 2. So now I have this, right? This whole thing represents everything inside of these two parentheses, right? Those two binomials. But now I got to bring down this x term. And then what do you think I'm going to do with the x? Right. I have to distribute it. Oh, man. And look what happens when I do my first distribution. X times x squared is going to be x cubed. I'm not really even going to continue because I now notice I have an x cubed term. So this thing is not a quadratic function. Okay? So again, as you can see, we might have to mathematically manipulate $7.10 our function in order to kind of see whether it might be a quadratic or not. And I think kind of putting it maybe into the standard form might be the easiest way to look at it. So thank you so very much for joining me on this deep dive into the world of identifying quadratic functions. Now, the way to get better at something like this is to do a lot of practice. And guess what? We got you covered. I have a whole website dedicated to just that. We've developed the learning platform just for you to do a ton of practice problems. That's the way you're going to get better at this. And you know what? We're going to be there every step of the way. You'll never be without us. You'll never be learning alone. And we would love to help you through your class. So go on over to glazersguide.com and check it out for more practice and more fun. See you there.
For more practice and for more fun, go to glazersguide.com.
And for more practice and for more fun, come on, go to glazersguide.com.